it's not just the first time for us, for her, to be part of Laracon India, because she was there in last year as well. And everyone loved it. And then we requested her that we want you to be back again next year. So she's coming here. She has been from Brisbane, Australia. She has been one of the Laravel core team member. And every time when I think of her, it reminds me like my pulse, like, because it reminds me Laravel Pulse as well. So ladies and gentlemen, boys and girls, please welcome one of the most prestigious Laravel core team member, Jess Archer from Team Australia.
My name is Jess Archer. I'm on the Laravel core team. Sorry I missed you yesterday, but today feeling a bit better, so I'm very, very glad to be here and see you all. So today I am talking about Laravel Pulse and behind the scenes of Laravel Pulse. Okay, so this is a behind the scenes tour of how we built Laravel Pulse. But really, this is, hang on, clicker. This is a talk about data aggregation and query performance with large data sets. So for those of you that don't know about Laravel Pulse, it's a free open source package we launched last year, and it gives you insights into your Laravel applications. So it shows you things like the application usage, the queue usage, and then things like slow queries, slow requests, slow jobs, all that sort of stuff. And then it also gives you like the CPU stats of your servers. You can have multiple servers, and then you can view the data for the last hour, last 6 hours, last 24 hours, and last 7 days. You can also create custom cards, and there's a lot of cool cards in the community that people have created already. So let's talk about the challenge. So this was originally Taylor's idea, and when he kind of just gave me this very brief overview of what he thought it could do, these were some of the challenges that was kind of concerning me. So the first one is that we would need to capture data from every single production request. And we wanted to be able to handle an app the size of Laravel Forge, and we get about 2 million requests per day. So we wanted to make sure we could at least handle that. And we also wanted it to be easy to self-host. So we didn't want to use any sort of technologies that were hard for people to host on their own servers. So to start off with, we're going to talk about the slow requests card. So this card shows you requests coming into your application that are under a certain threshold, so by default 1,000 milliseconds or 1 second. And it'll show you how many times it was slow and what the slowest one was for each request. So the first thing, I was a little bit apprehensive about using MySQL to capture all of this data. So we'd used MySQL for Laravel Telescope, which is a local, like intended for local development. And when people had run that in production on their large apps, it was a lot of data to collect. So first thing I did was, can I do this without MySQL? Can I do it with Redis? So there's a lot of different data structures in Redis. It's a lot more than just like caching values. It's a lot more than storing strings. It has a lot of different data structures. But the data structure that stood out the most is Redis sorted sets. So the Redis website defines a sorted set as a collection of unique strings, which they call members, that are ordered by an associated score. So if you're familiar with a set in kind of programming, every member has to be unique. This is that, but then they all get a score associated with them. So this is an example of what a set might look like, where our members are strings that represent the routes. And then the score here could be the slowest time for that route, or it could be the count of times it was slow. So you tend to use a lot of keys to store information because the sorted set really just has these two columns. So let's talk about how we would do this for our slow request card. So we can use the zadd command in Redis and provide our key, so in this case, slow request durations. And zadd has a lot of cool little arguments you can provide to it. So in this case, we're using GT, which means greater than. So we're going to say only update this member in this sorted set if the new score of 1347 is greater than the existing one. So it'll always store only the slowest one. We then create another key to store our counts, but this time we only want to increment the count by 1 every time this route is slow. So it's going to always increment by 1. And one of the great things with Redis is if this key doesn't exist, it'll automatically create it, and if the member doesn't exist, it'll automatically create it. So next up, we have another slow request come in. This one is a higher, this is greater than, so we're going to expect our sorted set to get updated and our count to be incremented. And then we have another one come in. This one is less than, so we're not expecting our set to be updated, but we still want our count to get updated because they are still considered slow. Now, to retrieve these values, we can use the zrange command. So we would call our key slow request durations. We just want the top 10, so we're going to say 0 to 9. We want them in reverse order with rev, because by default, a sorted set is from lowest to highest score. But we want them in the reverse order. And we want the scores as well, so we say with scores. So this gives us now, from our sorted set, our members and our scores. And this was our slowest score from our example. Now, in order to get the counts for how many times they were slow, we have to use ZM score. So the reason we can't use zrange again is because the top 10 by count might not actually match up with the top 10 by the slowness. So we use ZM score, and we pass in all of the top 10 keys that we got from our zrange command, and then this will give us the scores for those members, and we can join that data up together. This does introduce an interesting, hang on, sorry. Yes. The biggest problem with this is that this only gives us a score from effectively all time, or whenever we started capturing our data. So if we want to look at data for just the last hour or just the last 6 hours, we can't do that with this approach. It'll only give us the scores from when we started collecting or entering data into the key. So there's another approach that we can use, which is to divide the data into smaller buckets. So in this example here, we've got the data divided into 1-minute buckets. So if you imagine each of these sections here is one sorted set, one key, and we can keep the data for that, which means that we can then union those keys together and get the scores for just the last hour. And this works kind of okay, but there's this interesting problem here. Most of the time, the buckets aren't going to fit neatly in because we're not going to be at the start of the minute, we're going to be partway through a minute. And so if we include that top bucket, then we've got inaccurate data because it's counting stuff outside of our period there. And if we exclude it, it's also inaccurate. The bucket at the bottom is fine because that bucket's only half full at the moment, so it's kind of up to date. So it's just that top bucket that's causing a problem. So let's do a summary of Redis sorted sets. They are perfect for leaderboards that start at a fixed point in time. They are ridiculously fast, both writing to and reading from a sorted set, lightning fast. Minimal data is stored, so it doesn't store data for every single entry. It's just keeping track of the results effectively. It's pre-aggregated. And it makes it really easy to add custom cards because those keys don't need schemas and database migrations. You can just start writing stuff to keys that don't exist, and Redis will create them for you. But as we said, there's no way to query different time periods, and bucket strategies either reduce accuracy or they have a hard fall-off. The other thing I forgot to mention is that every time a bucket drops off the end, say for the counts will drop all of a sudden and then build back up over the minute and then drop again. And that's not great when we're looking at our data. Now, there is another Redis dataset called Redis time series, which looks really promising. But Redis time series is not part of a standard Redis server. It's part of this thing called Redis stack. And it's not available when you're using most hosted Redis services. So we had to rule that one out, unfortunately. As I said, it increases the barrier for self-hosting. So then we thought, well, how bad can MySQL really be? Is that actually as bad as a problem as we think? We're not going to collect as much data as we were with Telescope. This is really just these smaller stats. So let's look at the slow request card now in a MySQL kind of way. So this time we've got our Pulse requests table, so it's kind of like eloquent style, where we have some attributes for each request coming into our application. So in this case, we've got request. We've got a user ID to say whether this one is authenticated or not. And then we've got the route. Now, this time we're storing it as a little JSON tuple. This just makes it easier to pull the data apart later, but it's not a JSON column. And then we store the duration of this specific request. So next request comes in. This one's not authenticated, so the value is null. It's the same route, and it's got its duration stored. We have another one come in. This one is a different route, and we're storing its duration of 32, and this one was also authenticated. So we've got an idea of the data we're working with. So let's look at how we would query this to find just the slow requests. So we've got this SQL query, and I'm going to walk through this in a bit of a funny order because SQL kind of, I don't know, to me is in a funny order. So the first thing we care about is that we're selecting data, something, from the Pulse requests table. Now, we only want to consider rows where the duration is greater than or equal to 1,000, so that's our configured threshold, and where the date is greater than or equal to the start of the period we're interested in. So the start of the last hour, like 1 hour ago, 6 hours ago, so on and so forth. We want to group that by the route, because we're going to aggregate the data on a per route basis. So we're going to group by the route. And now we can select the route. We can select the max duration of that group and call that the slowest. And then a count of all the records in that group to get the count of times that it was slow, that it was over that 1,000. We're then going to order by the slowest descending, so we get the slowest at the top. And we're going to limit 101. So we decided we wanted to show a maximum of 100 slow cards, slow requests on the card. But we wanted to also let people know if there were more than 100. We didn't want to run an extra query to actually count how many were there. We just wanted to have a little indicator that's limited to the first 100 records. So by selecting 101, we only show 100, but we kind of already know that there's at least more than 100. So if we run this query, we get our route, the slowest of all the times that it was slow, and the number of times that it was slow over that threshold. So this works pretty good, but there are a few problems here. So our slow request table has got every request the application has seen. So we're talking potentially millions and millions of rows, and we're just trying to find the slow ones. So if we look at this duration column here, where we're saying where duration is greater than or equal to 1,000, even with an index on this column, this is a lot of work for the database to do to narrow down the rows to just the ones we cared about. So how did we solve this? We added an extra column to the database. This is kind of a pre-computed column of whether or not this request is slow or not. So 1 or 0, true, false. So we calculate this ahead of time when the data goes into the database. And that means now our query is just where slow equals 1. And this is much more efficient for the database to perform with our index on that column because it's a Boolean column, 0 or 1, so it can effectively automatically almost get all of the slow records instantly. Now, let's talk about this group by route here, because this was also a pretty big problem. So the route column, you can imagine the routes could actually get quite long. And in other scenarios, we're storing SQL queries or the URLs of outgoing queries. And those are going to be probably more than 255 characters. So we couldn't use a varchar column. We had to use a text column. The problem with a text column, though, is that you can't create an effective index on a text column for the purposes of grouping. So when you create an index on a text column, you've got to specify how many bytes of the data to consider for indexing. But as we're grouping, we only really care about are two rows equal. We don't need to do any partial searches on those. So how do we solve this one? We had another column here, another pre-computed column, which is the route hash. So this is an MD5 hash of the route column. The great thing about MD5 is it is always 32 characters long, so we can store it in a fixed length column. And we can then create effective indexes on it because it's a nice small column. So we can update our query to say group by the route hash instead. Unfortunately, we also have to select the route hash because it doesn't like us selecting an ungrouped column or an unaggregated column. But it's pretty straightforward once you've got the results to map the route hashes back to the routes. So how do we create this route hash column? Well, we could compute it in PHP, or we could have the database do it for us. So here's an example of the create structure for that table, where we have our route column that's a text column, a route hash. Now, it's a MD5 hash of the route, but we can actually store it in a binary 16 column, just due to the way that, because MD5 is hexadecimal characters, 32 hexadecimal characters, each pair of characters effectively can go down to one binary number, so it just means we can store it in a really small space. And there's a great article on the Planet Scale blog by Aaron Francis that goes all over this kind of approach and when you might use it. All right, let's talk about the application usage card now. So this is showing you how many users are hitting your application. This one doesn't really show you a problem like the slow request one. This is just showing you activity. All right, so we've got our exact same Pulse requests table as we had before. This time we only care about the date and the user ID. We don't need any of that other data to calculate the stuff for this table. So if we look at our query for this one, again, we're coming from our Pulse requests table, where our user ID is not null, so we only care about authenticated requests, and where our date is greater than the start of the period. Grouping by the user ID, we're going to select that user ID and then just select the count. And then we can order by the count, descending, and grab our 10. So in this case, we're always just showing the top 10. If we run this, we get our user IDs and our counts, and we can map the user IDs to information to show in the user card. Now, unfortunately, this query is about as good as this one can get. But this is going to be, one of the biggest problems is this, is that in order to know the top 10 users, we've got to calculate the count for every user in the system across millions and millions of records, just so we know, so we can sort it and get just the top 10. And when we ran this with our Laravel Forge data, this query would time out. So this was a problem. All right, let's talk about one more example. This is the CPU information. So this is just graphed data. And what we found here is we wanted to show 60 points on the graph. That seemed to be a good number. If you put thousands of points on the graph, it was just too choppy and too much information to use to give to a JavaScript charting library. So we wanted to do 60 points, regardless of whether you're looking at an hour or 6 hours, 24 hours, 7 days. So let's have a look at how we store the data and generate this one. So we're going to capture data every 15 seconds. So even though we only want to show 60 points, we want to have data taken regularly that we can then average. So at 11:27 here, we've got our server web01 has recorded its CPU percentage of 22 and its memory. We're not going to be using the memory at the moment, but it lives in that table. 15 seconds later, we then capture the CPU again at 47%, and then 15 seconds later again, 15 seconds later again, and then now we're at the start of a new minute. So we've got our CPU record there. All right, so how do we condense this down to 60 data points? Actually, first let's talk about how many readings this gives you. So with this approach, you will have 240 records per hour per server. So that's one every 15 seconds, which means you've got 1,440 in 6 hours, 5,760 in 24 hours, and 40,320 in 7 days, again, per server. Now, this isn't a huge amount until you look at what we need to do with it. So how do we get those 60 data points from all that data into those 60 average data points? So let's start off with a real basic query. We're just going to select the date, the server, and the CPU from our Pulse service table, and we've got our data from every 15 seconds. Good to go. All right, how do we divide this into smaller chunks? Well, the first thing we do is we get the Unix timestamp representation of the date. So we're just going to select that here. I'm going to build this up a little bit. The Unix timestamp is the number of seconds from a fixed point in time. And so you'll see these numbers are all 15 seconds apart. It doesn't really matter when the point in time was that it started, but it was 1st of January 1970. All right, so the next thing we do is we divide this number by 60. And now you'll see what we've effectively got is the number of 60-second periods that have elapsed since that fixed point in time. So the number of minutes that have elapsed. So our first record here that's on the top of the minute is a whole number. And then we've got these decimal numbers all the way until we get to the start of the next minute when we're back to a whole number. So if we want to group all our minute data together to show one data point per minute, well, what we can do is we can round down that number. And so now all of the readings for 11:27 now have the same number, and 11:28 has a different number. Now, this is all we need to do in order to be able to group the data into these larger chunks. But just to demonstrate what's happening here, we can then multiply this number by 60 again, our rounded down number, and that turns it back into a Unix timestamp. And you'll see our first 4 are still all the same number, and then a new number for our last one. And then we can turn that back into a date if we really want, and see that we've got all our 11:27s and then our 11:28. So how do we bring this into our query to make this work? So again, from our Pulse service table, where the date is greater than the start of the period, we want to group by the bucket and the server. How do we calculate that bucket? Well, we use our formula here. So then we're going to be grouping all those records into one, and that way we can then just ask for the average of all the records for that 1 minute, and then we get our results here. So we've got one result for 11:27, one result for 11:28 with an average CPU of all the records from that 1 minute. So why 60? It's a little bit confusing what that number, or like maybe the significance of it. So the reason we choose 60, so if we look at our 1 hour data period, that has 3,600 seconds in 1 hour. If we want to divide 1 hour into 60 chunks, then that will give us that number 60. So we want to show 60 points on the graph, and it happens to be that with an hour, when we divide the number of seconds in an hour by 60, of course, we get 60. So our bucket size is 1 minute. But for our 6 hour period, there's 21,600 seconds in 6 hours. So when we divide that number by 60 to divide it into 60 pieces, then we get 360 seconds, which is 6 minutes. So the bucket size in that case becomes 6 minutes. We could do it again for 24 hours, where we get a 24-minute buckets. And then for 7 days, each bucket is 2 hours and 48 minutes. So let's summarize how MySQL helped us here. So it allowed us to query any time period we want. That's good. But aggregation is still slow with millions of rows, even with really good indexes. And custom cards would become a problem because anyone creating a custom card would need to create their own migrations to go with their custom card. So then we started to wonder, is data sampling the only solution? We always had this in our back pocket that if Pulse was too slow on large apps, we could allow people to sample just some of the data, so maybe 10% of requests or 1% of requests, depending on how large your application is. But we didn't like that this was going to have to be maybe the default thing you'd have to use on something the size of Laravel Forge. We wanted for at least that size of application to be able to work at 100% sample rate. So then we came up with this new idea, which we're calling pre-aggregated buckets. And you might say, wait, wasn't this the problem we had with Redis? And yes, it is, but we're going to talk about how we solved it uniquely with MySQL. All right, so let's talk about how we would do pre-aggregated buckets with our CPU readings, because they're a pretty good example here of dealing with just bucket data. So at 11:31, we've got a CPU reading of 22%. So we're going to create this new table called Pulse Aggregates, just a generic table to store aggregated data. And for this one reading, we're going to create 4 rows to store this data. Seems crazy, I know, but you'll see where it goes. So we're basically creating a new row for every for each bucket. So for the time, when the time is 11:31, the start of the bucket for the 60-second period is 11:31. But you'll see these other buckets here, they go further back in time. So we've got our 7-day bucket down the bottom. If the time is 11:31, those buckets were 2 hours and 48 minutes, so the start of that bucket happens to be at 10:48, and we'll get a new bucket 2 hours and 48 minutes after that. So in this table, we're also going to store the type of data we're collecting, because it's a generic table, so in this case, CPU. And then we're going to capture the key and the key hash. So this was kind of like the route in that other table. It's that extra piece of data you want to group by to divide the data down again. In the case of servers, they're probably not going to be longer than 255 characters, but we're going to store all sorts of data in here, so we went ahead and created the key hash column straight away. And then we're going to store what type of aggregate we're storing here, because we might want to store multiple types of aggregates for the same type of data. We can then store the value, so this is our 22% that's just happened, and then the count of records that this table is representing, and we'll see why this becomes more important later on. So then 15 seconds later, we have a new reading come in at 47%. But instead of creating 4 more rows, we're just going to update these existing rows that we have here. So we're going to update the average to be the new average. So the value in here is not going to be 47. It's going to be the average of the previous record and then the new record that's come in, which in this case happens to be 34.5. So then 15 seconds later, we're going to update that record again. We're going to incorporate our new reading into this rolling average. And then 15 seconds later, same again. And then at 11:32, something different happens here. We get a new bucket for our 1-minute period, and we no longer update the bucket for that 1-minute period before. And you can imagine if we continue this forward, eventually the 6-minute bucket will close off and a new one will be created, and then eventually even the 7-day one will do that. So what does this get us? Well, those 40,320 rows that we had now collapse down to just 240 rows. So there's 60, we only need 60 rows per period to capture that data, and we have 4 different periods, so 60 times 4 is 240. So that's a 99% reduction in rows. Now, let's talk about how we populate those aggregates, because we were kind of sometimes inserting, sometimes updating. So for that, we use upserts. So upsert stands for update or insert, so it'll insert the record if it doesn't exist, or update it in some way if it does. The Laravel Query Builder supports upserts out of the box, but by default, it will replace old values with new values. In our case, we want to incorporate the new value into the old value rather than just flat out replacing it, which is what I just said there. So in order to make this work, we need to create a unique compound index on our Pulse aggregates table to say that there can only be one combination of a bucket, period, type, key hash, and aggregate. That is where that uniqueness is defined. So if a new row comes in with the same ones of those, it's not going to allow that to go in, and therefore it's going to update the record instead. So we can now look at our upsert query. This is for a sum. So if we were wanting to sum the number of things that have happened, so we would use this for our user requests, for example. So first thing we need to do is insert into our Pulse aggregates table our bucket, our period, our type, our key, our aggregate, and our value. We don't need to insert the key hash because the database is going to do that for us, and that's going to cause that collision. So then we're going to insert our 4 buckets for this thing. So our 1 hour, our 6 hour, our 24 hour, and our 7-day data, where our type is user request, the value is 42, and it's the sum aggregate, and the value is just 1. We're just increasing it by 1 each time. And then this is kind of where the magic happens, right? So on duplicate key, so if that key already exists, we're just going to update the existing value to be the existing value plus the new value that's just come in again. So in this case, it's going to be incrementing it by a certain number. So let's look at how the max one would work. So once again, we're inserting those same columns. This time we're inserting slow request data. So we want to say we only want to update this record if the new score that's come in, 1431, is greater than the previous score we already have. And so to do that one, on duplicate key, update the value to be whatever is greater, the existing value or the new value that's just come in again. And we'll look at one more example, because this one's kind of cool. So this is how we do our rolling averages. So this time we're inserting one extra column, our count column. So this count column is only needed for averages, and we'll dig into why that is shortly. So we're going to insert our data. So this is for our CPU readings. So we've got our 21% in this case, and we're always going to set the count to 1. So that if this record gets inserted from scratch, the count will be set to 1, because that's the first record. And if we look at the on-duplicate key here, we can see we're updating the value with this kind of complicated little expression going on here, and then we're increasing our count to be the old count, just plus 1. Now, in order to dig into how these rolling averages work, I think it's a bit easier to talk about it in PHP. So let's talk about first how averages work in general, which I'm sure most of you probably already know. But if we have a set of values, 1, 2, 3, and 4, the first thing we want to do is get a sum of all those values. So that would be 10. We then want to get a count of the number of values, so that will be 4. And so our average is equal to the sum divided by the count. So the average in this case of those 4 numbers is 2.5. But you'll notice that in order to calculate this, we need to have all of the values that went into it. But with the approach we're talking about here with the pre-aggregated buckets, we're not storing all of those individual entries. We're just storing just the result, just that 2.5. So how do we incorporate the new number in? So let's imagine we just have the count and just the average, and a new value of 5 comes in. So the first thing we can do is calculate what the old sum was by multiplying the average by the count, and that turns it back into that 10 number. We can then get our new sum by adding the old sum and the new value, which gives us 15. And our new count will be the count plus 1, so now it's 5. And so our new average will be the new sum divided by the new count, and our average in this case is 3. And so that's how we can apply the rolling average in the database, by just making sure we capture the current average and also the count of values that went into it. Now, one thing that's important to mention, I don't want to spend much time here, is that we do trim the data that goes in, because we only need a certain amount of data to generate all of our graphs. So for our 60-second periods, we're only going to keep those for 1 hour. For our 360-second buckets, we're going to keep them for 6 hours, 24 hours, 7 days, etc. All right, so how do we retrieve the data for graphs from these aggregates tables? This gets really easy now. So we're just going to select the bucket, the key, and the value from our Pulse aggregates table, and we've just got a bunch of where. So where type is CPU, where the period is 60 or 360 or 1440, and so on, where the aggregate is average, and the bucket is greater than or equal to the start of our period. There's no more group bys required, no more average, like AVG kind of things required. Those are the things that make the query slow. Now we can actually just select the exact 60 points we want, and we'll get back 60 rows with no aggregation whatsoever. And so this query is now lightning fast. We get our results here, where each record is set 1 minute apart. But in this case, those buckets are what we already created earlier. So we don't need to do all that complicated math to figure out the bucket in this query, because we just figure that out when we're inserting the data now instead. So it's pre-aggregated. So how do we solve the bucket problem though? So as a reminder, that's when this happens. So we've got, when the time is partway through 11:20, for example, we've got this bucket at the end that we want some of the data in that bucket, but not all of it. What we really want here is just this part of the bucket here, which we call the tail of the data. So in the database table, that might look like this. So this is looking at a 7-day view of data, and we've got our record at the top there that has some of what we want, but not everything. We just want all these green ones, but we still want a little piece of that red one. So how do we do that? Well, we actually go ahead and store every single entry that happens. So we're kind of back to where we started, right? So now, for every slow request, we're going to capture all of that data for every single slow request, and we're going to be capturing it in its aggregated form as well. But we can combine this data together, and don't worry, I'm going to zoom in on this one. So let's dive into our subquery here and look at how we would query the tail. So we're going to select the key hash. Let's go through it like this. The key hash, this max value to get the slowest one from our entries, from the entries table, where the type is slow request, and where the date, this is the part that's important. So we want records where the date is greater than or equal to the start of our window. So let's say if we're wanting to go 7 days ago, so from 7 days ago, and where the date is less than the start of our first whole bucket. So this will give us just the records from that little tail period. We can group that by the key hash. We can then union this data with the data from our buckets or our aggregates table. So again, we're going to select the key hash, the max value. So here we're actually aggregating data that was already aggregated, because we're trying to collapse this down now into like all of those buckets. We don't need them for the graph, or we want them spread apart. We actually want to collapse them down into single values. So from our Pulse aggregates table, where the type is slow request, the period is the period we're interested in, the aggregate is max, and the bucket is greater than or equal to the first whole bucket. So this will give us just those full buckets that we cared about. We'll group that by the key hash, and then we're then going to group those key hashes again, because the same record might exist in the tail and in the buckets. And so now we can select the key hash once again and get the max of all of the maxes. So we're aggregating aggregate data that was pre-aggregated. There's aggregates going on everywhere. And then we can order by the max descending, and finally get our 101. Now this seems like a lot of work to do. You would not think that this would be more efficient than our more simple queries. But we have drastically reduced the amount of data that needs to be considered, and reduced the amount of data that needs to be aggregated on the fly. Those buckets have kind of pre-aggregated most of those things and made this much, much quicker and smaller. So the result of this query, we get our key hash and our max value of the slowest route, and then we can run an extra query to convert that into our route, and we'll get our results there. So let's talk about the numbers when we ran this on Laravel Forge. So if I run a select count star from Pulse entries where type equals user request, then we've got roughly 12 million rows in that table. But if we divide that number by 60, so we get 1/60th of that data, or the size of the tail, or the maximum size of the tail. So the tail is kind of interesting. At the top of the minute, the tail is nothing, it's tiny. But as the minute grows, or as the bucket size grows, in the case of a larger one, the tail gets bigger and bigger. But the largest the tail can ever be is 1/60th of the data. So we've got 205,000 rows from Pulse entries we need to consider. And then if we look at the aggregate data for all of the aggregates for the same user request, we've got 153,000 rows. So why is this good? Well, previously, we would have needed to consider all 12,341,781 rows. Now we only need to consider approximately 360 rows at max for the size of Laravel Forge, which is a 97% reduction in the data queried. And it made the query that previously timed out now run in a second or so. Thank you. Now, we created an API to wrap all this up. So this is what we use internally, but if you create your own custom cards, you can create all this data with just this simple method, this pulse record method, where you pass in the type you want, so that maybe that's CPU. The key is your kind of subgrouping thing, so maybe it's the name of the server, and then the value. And then you can chain on as many of these aggregate methods as you want, and this will cause that data to get pre-aggregated in the aggregates table and also saved in the entries table. So this is an extreme example where we're doing all of these different aggregates just to show you what's possible. So in this case, user sale, you might want to record all of the sales in your system with the user ID as the way you group them so you can view them by user, and then the value of the sale. We then created an API for querying this data. So this is what you'll use inside your Pulse cards. So we've got a few different methods that will return the data in different shapes. So we've got an aggregate method, aggregate types, aggregate total, and graph. They all query the same data, but they just return the data in different shapes. Some of them can query multiple aggregates at once, and some of them can query multiple types at once. Now, the last thing is, you might be thinking that that is a lot of upserts to be doing. At the end of every request, you're going to have at least 4 rows, but if you've had a slow request and a slow job, all these things are going to be adding up. So that could be a lot of upserts. And so that's why we also ended up using Redis, purely optionally. You can use Redis to ingest your data. So the thing to know with Pulse, I guess, is that even when you're only using MySQL, all of that data insert happens after the request has been sent to the user. So it shouldn't impact the speed of your application. However, it does mean that that process is still doing a little bit of extra work at the end before it's free to go and answer the next request. With the Redis ingest, we can just dump data onto a Redis stream, lightning fast, and it'll get pre-aggregated in a background process. So to enable the Redis ingest, you just set this configuration option, Pulse ingest driver, set it to Redis, and then you just need to run this worker, PHP artisan Pulse work, and that'll do all of the aggregating then in the background. Now, for most apps, you probably won't need to do this. We do it on Forge because we wanted to make sure that as little work as possible is happening inside the request and push that off to the side. So it's a good thing to reach for, but I wouldn't reach for it by default. Now, if that's still too much data for you, well, as we mentioned previously, there is always sampling. We still added that feature in. So if you've got an app that's bigger than Forge and you don't want to increase the performance of your database, you can always enable sampling, and you should be good to go. Thank you very much.
Thank you. Thank you, Jess. Happy to see you full of energy. So, a couple of questions. Happy to see you full of energy.
Energy, yes. I have some energy.
Yeah. So how do you feel coming back on Laracon stage once again?
It is fantastic to be back. I was really disappointed yesterday when I wasn't feeling well, and I really wanted to come and see all your beautiful faces and just hang out with everybody. So I just put a lot of effort into sleeping and recovering and made sure that I could be here for my talk today and to hopefully spend the rest of the day with you all as well.
Yeah, perfect. And also one more thing, we are planning more sort of like Laracon World Cup. So if we get time during the conference, then we are planning the cricket match between India, England, and Australia. She's the captain of England team. We have a captain of England, so from the Australia.
Captain of Australia?
Yeah, and from the England we have Joe Dixon. So we'll plan something. Now looking at the questions.
Okay.
You got the maximum questions. I think there are more than 30 questions. I don't know which one to pick, but let me pick any random questions. So the one question is like, the limit of 101 was very smart. Is it good idea to create custom paginations like this in an infinity scroll-like feature?
Sorry, I'm having trouble thinking of the question. So limiting with the...
Yeah, this is the question. Like the limit of 101 was.
Oh,
very small.
yes. Is it a good idea to create custom? I think that could actually work quite well for infinity scroll because all you really need to know is that have I reached the end of the list yet? So by getting one more row than what you know you'll need, you at least know that there's one extra row. If you ask for 101 and you just get 100, then you know you can show the end of the infinity scroll. So I think that would probably work. The only disadvantage is it doesn't tell you how many rows there are, but normally you need to run a separate query, and these queries can be expensive. If it's not expensive, run the separate query to get the count. But if you're like needing to save time, then yeah, that's a cool approach.
Perfect. Second question. I was implementing Laravel Pulse in one of our projects, but it is API using Centrum. Hence, I was unable to get Pulse working on production. What can be the solution for this?
So, I mean, I can't think off the top of my head any reason why you shouldn't be able to run Pulse on an API-only thing. I mean, Pulse is going to have a web route for its dashboard. So I guess there's a few things you could do. You can still have a web route in an API-only service, but you can also host Pulse entirely separately from the rest of your application. So you can have it on a dedicated database and a dedicated web server so that nothing to do with the dashboard will impact the rest of your application. And if you've got different technology requirements, so yeah, either of those should be fine. Perfect. If there's a bug though, open an issue on the repo if there's an actual bug, and we'll look at it.
Yeah, we still have to spend a lot of time with everyone because so many questions. Thank you, Jess.
Thank you very much.
Thank you for being on stage. Big round of applause for Jess to make sure everything is rocking on stage.